Hello and welcome to the Introduction to VCE Physics Unit 3. My name's Noah Bajeo and I will be taking you through this physics course, and I look forward to having you along for our journey. All right, a little bit about me. I studied physics in 2020 and achieved a raw score of 48. I received the subject award at my school and I got an ATAR of 99.75. So I think I know my stuff, and hopefully I'll be able to share a bit with you and a little bit of tips and tricks to get you through physics. At the moment, I'm studying commerce computer science at Monash Uni. I love sport, and I particularly like cricket and sailing. Those are my two kind of sports. And I've got hobbies in finance and science. So this kind of stuff helping you with physics is right down my alley. All right, so let's get on to some important stuff. What are we going to do? Well, I have for you some important links to the car website, which hopefully you'll be able to use quite efficiently. I find one of them particularly useful, and I found it that a lot of people didn't actually know that it existed. So maybe you get a little bit of an edge. We're going to just have a quick recap of Physics 1-2 before going into Newton's laws of motion and constant acceleration. All right, here are those important links. So we've got the study design, we've got the formula sheet, both of which are pretty self-explanatory. The study design tells you what you need to learn, what you're going to learn throughout the year. All of our presentations here at Air Learners are done in accordance with those study designs. So hopefully I'm teaching you what needs to be taught. That formula sheet you get in the exam, and you should also get in your SACs. It helps you just in case you forget a formula and you don't have to put it on your cheat sheets if it's already there. Personally, I included lots of stuff that was already on the formula sheet in my cheat sheet just because I found that I could write extra notes on all of those things. And the really useful thing is the VCE glossary of selected physics terms. Now, it's not actually called that, that's what I've called it, but let's just have a quick look to see what it is. All right, so here we have the advice for teachers page, and on it we've got a couple of important bits. We've got the link to the study design, and we also have along here quite a few interesting bits. So the bit that I like the most is the terminology in the study design. That's quite good for clarifying some things, but there's also another one in measurement in science that is very useful. Measurement terms: accuracy, precision, repeatability, reproducibility, and validity are all really key parts of the course. You've got to know what they mean, and that is really, really useful if you want to do well in your pracs. And a whole other bunch of stuff in here. I don't have to take you through them all. You can explore it yourself. I'll put this up on with the PowerPoint, so you'll be able to access it. If not, you can just search up advice for teachers physics, and it should come up pretty straightforward. And then there's also the past exams and the examiner's reports, which you'll probably end up doing towards the end of the year. All right, so let's just go through a quick recap, just perhaps to refresh your memory. So first of all, an FBD is a free body diagram. Pretty much what it means is you draw something and then you label it with everything that's relevant. So for instance, if I was to draw a box, a mass, then I'd write the mass inside of it. Say it was 100 kilograms, I'd write that in it. Then I'd also draw all the forces acting on it. And that just kind of helps you picture what's going on and helps you tackle a problem. You'll find that I often bring this up just because I do think it's very important, and it helped me do quite well. So I think hopefully it'll do that for you as well. Quick thing about forces and vectors. So a quick thing about forces and vectors. So solid lines is what I'm going to be using for individual forces. That is, generally speaking, the convention. So we'll stick to that. And we'll have a dotted line for the net force. And now when I talk about the net force, I mean the addition of all the vectors using, you can use the head and tail method, you can use the parallelogram method, whatever you've been taught. If you have any questions, you can ask your teacher, you can ask me via the Air Learners page, but it's pretty straightforward and you should be able to get it pretty easily. Now, assumed knowledge, this is quite important because if you don't understand this, you may get a little bit stuck. I'll try and make it easy to understand, but you should know trigonometry to a year 10 standard. Going further than that would obviously be helpful, but it's not necessary. The understanding of Pythagoras' theorem, which I believe is year 9, so hopefully you know that. And also kind of a basic understanding of the physics 1-2 content and its application. So we'll just go over a couple of examples perhaps to start off throughout the course. But otherwise, most of that is assumed knowledge. If there is something that you think needs to be included in there, by all means get in touch. Newton's laws of motion. So there are 3 laws of motion that you can see. First, I'm just going to go. So the first is that an object will stay in motion and it will continue to do so until it's acted upon by an external and unbalanced force. So what that means is if I push something that's unbalanced, there is nothing acting back on it, and so it will start to move. The next second law, which is perhaps the most used law of all of them, is that the net force is the product of the body's mass and acceleration, so F equals ma. Now note the importance that I've included of this summation sign. And you'll see that I'll use it throughout the course. It means that's the collection of all forces, and it's commonly misinterpreted as a single force is the mass times acceleration, but it's actually all the forces combined that give that mass times acceleration. And that's quite important. That's often where a lot of people make mistakes. Next is that forces do not act singularly. They act in pairs of equal magnitude and opposite direction. So what a lot of people also miss is that they act in pairs. So that's relatively important. I would highlight that in your book. I'm going to do that here because a lot of people don't realize that, for instance, weight force is countered by a normal reaction force of the ground pushing back up on you. So that's another important thing. The first law, inertia is something that we experience all the time. So that's the first law in one word. And it's a concept that can be quite useful when understanding come exam time, as it's often required to explain certain phenomena that we'll go through in future lessons. So examples of that is like when a car accelerates or brakes suddenly, we feel that our body wishes to continue along in its original velocity. All right, next part of Newton's laws of motion. And this is kind of a format that you will see as a recurring theme. I'll give the formula and then I'll explain what each of the things in the formula means. So F equals ma, we've already kind of discussed that. So the sum of the forces is ma. So F is the force. In newtons, it's a vector, so it has direction as well. So I'm just going to chuck a little v next to that. M represents the mass. Now mass doesn't have direction, so it's just a scalar. And A is acceleration. It does have a direction, so it's also a vector. So that can be something you might want to note down. You don't have to, it's not necessary. So there are also 2 common mistakes, is, as I've already said, not including the sum of all forces and only using one force. I've seen that happen to a lot of people in my class. I think I've made that mistake a couple of times early on, luckily managed to rectify it, but it's something that is certainly workable. You can work on it, and once you get it right, it becomes pretty straightforward. And then another thing is using only the acceleration and ignoring the mass altogether when finding the force. Probably a slightly less common error, but it's still something that happens a lot. I've seen it a few times. Again, I've made that mistake, so it's just about accuracy, making sure that you go over your work so that you avoid them. Now, this formula is probably the most widely applicable formula, in physics study design, so it's really important that you use it and know how to use it. All right, practice question 1. Box A is stationary on a flat and smooth surface. Question A, or part A, is label the forces acting on box A, and B is find the magnitude of the normal reaction force. Now I'll give you, it shouldn't really take any longer than a minute to do this, a couple of minutes perhaps, but you can pause the video and come back when you're ready. All right, now that you have had a go at that question, let's have a look at the answers. All right, this is what I've done. I've labelled the forces acting on box A. Now, as a convention, you don't necessarily have to label the forces from the middle of the object as long as it's touching the object, but I'll try have it definitely touching them towards the centre, I guess, that way. So as you can see, I have labelled over here the gravitational force and the normal reaction force. That's pretty standard notation. You'll see it over and over again. So each of those would be 1 mark. And the next is our magnitude of the normal reaction force. So we know that it's not moving, it's stationary. So we can say that the sum of the forces is 0. And that's also interpreted as Fn minus Fg. So the normal reaction force less the gravitational force is 0. And so substituting that in, because Fg is mass times gravity, which is 9.8 meters per second squared, we get the normal reaction force to be 25 multiplied by 9.8, which is 245 newtons. And because it says the magnitude, you don't need to state a direction, but always be careful, because if it doesn't say magnitude, you have to give a direction. So if the direction would be upwards, for instance. All right, so we're just going to touch on this now for the next couple of questions, but some basic kinematics formula that you should have learned in Physics 1-2 if you did it. If not, here it is for the first time. They're pretty straightforward, and you'll use them quite a lot. So I don't necessarily have to run through all of them, but just remember that S represents displacement. If you've done things like methods, specialist maths, you might have used X instead. Physics tends to use S, not sure why, just is. I've got U as the initial velocity, V is the final velocity, A is the acceleration, and T as time. The only one of these that is a scalar quantity is time. So everything else here has a direction, and that is important because a lot of people forget that sometimes there's a question of label each of these things as vectors or scalars. Some people forget that, for instance, displacement is the vector and distance is the scalar. So a core component of this study design is the application of these formulas, and we'll have a look at kind of more of these applications in the next few lessons, but we're going to need them for a couple of practice questions. All right, practice question 2. Given that the force is applied 60 degrees from the horizontal to a 25 kilogram box and has so force is applied 60 degrees from the horizontal to a 25 kilogram box and it has magnitude of 50 newtons. So resolve this tension force into horizontal and vertical components to the plane. Now I've helpfully included this axes, so that's what they mean by horizontal is the X and vertical is the Y. It's pretty classical in terms of layout, and this term resolve is something that you will find comes up more and more as the course goes on. But you probably won't get a question like this in the exam, but you'll probably get a question that requires you to do this step. It's quite generous at 3 marks. Probably wouldn't be worth 3 marks in the exam. If you were to do it, it would probably be worth 1 or 2 marks along the way, but it is important that you know how to do it. So simple trigonometry. Horizontally, we've got the tension force. So I've got Ft. That's my tension force. Is 50 times the cosine of 60 degrees. So that's 60 degrees is there. And from your trigonometry, you'll know that cosine is the adjacent side, which is this one, over the hypotenuse, which is that one. So that could be useful. And we get 25 newtons in the X direction. Now, notice that the tension is acting on the box in the arrow specified there. So I've given a direction because it's in the horizontal as well. All right, so vertically is the same kind of scenario, except we're multiplying by the sine of 60 degrees as opposed to the cosine of 60 degrees. So you get roughly 43 newtons. It is important to note that the use of significant figures means that we can only give two significant figures, which makes it 43. We don't leave anything in the surds or as continued decimals, much to my disappointment. That would be, for instance, 25 by the square root of 2, but we can't do that, so it's just 43 newtons in the y direction. All right, so hence find the acceleration of the box. That's part B, and then part C is find the time it takes the box to travel 10 meters with this force applied, given that it starts from rest. So there's two questions here. Let's just go through the first one. Pretty straightforward, again using Newton's second law, but I'll give you time to do it by yourself and then you can come back. All right, now that you've had a little bit of time to do these two questions, let's just go through it. First up, using that second law, it's always a good idea to state the equation that you like to use. It's often a free mark somewhere, so may as well do it. It's not going to harm anything. And then we just substitute in the values. So force applied was 25 newtons and the mass was 25 kilograms, which means that it's pretty simple. The acceleration is 1.0 meters per second squared towards the right. You will notice that if you were to use the y direction, you'd also have to account for the gravitational force and the normal force, and you'd find that it's not moving anywhere. So that's why the acceleration is only along the horizontal, and it's 1.0 meters per second towards the right. Now for that second question, we've got this formula which we've taken from a few slides back, S equals ut plus half at squared, and we can very simply just substitute in the values and then solve for t. That's exactly what we're going to do. We're going to say, so, well, the displacement is 10 meters, which is right here. The initial velocity is 0. It says it starts from rest, plus half at squared. Now, taking the a from over here, we can get 0.5 by 1 by t squared. So you get t squared is 20, and then t is roughly 4.5 seconds. Again, the significant figures means we can give 2. In terms of mark allocation, the first question you probably get 1 mark for these two steps here, and then 1 mark for the answer. And then for the second question, you probably get 1 mark again for these first 3, I suppose, and then another mark for your answer. All right, practice question 3. Lots of practice. In a lift, box B is on top of box A as shown. The lift is initially stationary and accelerates uniformly upwards. It reaches a speed of 10 meters per second after 5 seconds. Calculate the acceleration of the lift is part A. Shouldn't take you very long. I'll give you 20 seconds to do it. All right, now that you've had the time to do that, let's see what we can do. All right, V equals U plus AT. This is a little bit superfluous because you can kind of see it straight up, but we'll substitute all the values in anyway. So V is the final velocity, so it's 10. T is going to be 5, and U is going to be 0 because it starts from rest. So I rearrange for A, and you get 2 meters per second squared upwards. So there's your 1 mark, just to the answer. Make sure you include that direction because acceleration is a vector. Right, calculate the magnitude of the force on box A by the lift. Now this is quite a tricky question. It's one that comes up fairly often, I'd say. So give yourself 3 minutes to do this question. Might take a minute or so either side, but I reckon you've got this. All right, now that you've had a decent go at that question, let's see what I'd do. First up, I would say, well, the 25 kilogram box with the 5 kilogram box is essentially a 30 kilogram mass. And while it's the magnitude of the force on box A alone, box B isn't actually touching the ground. So all of its weight force is transferred to that 25 kilogram box. So it's essentially one 30 kilogram box. Now let's draw our free body diagram. And we've got the lift, force of the lift upwards, and the force of the gravitational, or the weight force of box A and box B combined, and that's what we get. We get that. You'll notice that the F lift is going to be much larger than this combined because it's accelerating upwards. So make sure that if you are drawing it and they ask you to draw it, that this bit is longer than this bit down here. So right, let's just keep going. As box B and A are both accelerating at the same rate, they're essentially connected bodies. This means that they can be considered as combined mass. And that's the reason for it. So that you don't have to write that as part of your answer. That's just me giving some explanation. But then we get into Newton's second law. So the sum of the forces is mass times acceleration. And now I'm using all these forces. So FL, I've just abbreviated F lift, minus the 25g plus 5g. So g is gravity, 9.8 meters per second squared. So I've combined those, so the 25 and the 5 becomes 30, which is this bit over here. And then the m is going to be this bit, and the a is going to be this bit here, as we found before. So keep going, and it's pretty straightforward. You get 30 times 2, which is 60, and then you add that to 30 times 9.8, and you get 354 newtons. And because it says magnitude, don't need direction, but it would be upwards. So given that the lift is in contact with box A, the full force is applied, some of which is transferred to box B so that they can both accelerate at the same rate. Hence the answer is 354 newtons. Right, so instead of boxes, a 30 kilogram child was placed on the scale in a lift under the same conditions. Explain what value will be recorded as the child's weight on the scales as the lift accelerates upwards and why this occurs. This is an explanation question, so I'll give you 4 or 5 minutes to do this. I always like to include calculations where they're appropriate, so that may be appropriate here. Good luck. All right, so now that we've had a good go at that question, let's have a look to see what I would do. This is the first thing I'd make. So the normal reaction force is greater than the gravitational or weight force on the child as the acceleration is upwards. That's pretty straightforward. That's what we saw in our free body diagram in the part beforehand. So given that the scales must react to keep the child in the same motion as the lift, it records the normal reaction force on its scales. And that makes sense quite logically. Everything has to be uniform, has to be all accelerating at the same time. If that didn't occur, then the child would just be falling through the lift, which obviously isn't occurring. And so this is the value that is the same as that calculated in 3b, as the normal reaction force in that case is the force of the lift on the boxes, such that the two boxes of total mass 30 kilograms act in the same way as the child of mass 30 kilos, which is 354 newtons. Now, a lot of people somehow manage to do all of this correctly, which is great, but then forget this bit, and that is worth 1 mark, because it's quite clearly saying what value would be recorded. So each of these points I would give 1 mark. Some teachers may decide to mark this differently because it is an explained question, but as long as you give a detailed explanation and use these terms like normal reaction force and the gravitational weight force, and then mention something about being in the same or constant or uniform acceleration, and then the comparison to the previous question, you should be fine. All right, we've finally finished. So let's just go through a quick review. We covered the following things. We did Newton's laws of motion. We did constant acceleration formula in 1 dimension with a specific focus on how that connected to Newton's laws of motion. And then we did an application of the theory that we learned with 3 practice questions. Thanks for coming along. In our next lesson, we'll be looking at all things circular motion, one of my favorite topics, including horizontal, vertical, and banked tracks. Thanks for your attention. I hope that you found this lesson interesting and that you learned something new. If you'd like to get in touch, feel free to go to airlearners.com and find me on the tutors page. Otherwise, thanks for coming along.